Today you're going to be learning about circles. We're going to identify special segments and lines in circles. Alright, so if you take a look at the right, we have a circle, and you've seen circles before. There's a couple ways that you can denote them. You have your center, and it's usually denoted by a letter or a point, and you can either write it as circle P, or you can actually draw the little circle with a point inside and P. That's how you can distinguish what circle you're talking about. Okay, so the different lines that are in a circle. If you take a look at the second drawing, we have the diameter that goes all the way across. It is also a chord. A chord is a segment whose endpoints are on a circle. So you can kind of think of a chord kind of like a guitar string or something. A guitar string chord. You have your two nodes, and then you could pluck the string if you wanted. So a chord actually has its endpoints on the circle. Okay, so we know that the diameter has to be a chord, and it also goes through the center of the circle. If you take a look right here, the green line, which I just made red, excuse me, the green line is an actual chord, but it is not a diameter because it doesn't go through the center. However, it does have two endpoints on the circle. Okay, we have the center of the circle, of course, because it's in the middle, and then we have a radius, which actually goes from the center of the circle to anywhere we want on the circle. Okay, so it's attached from the center to the outside of our circle. Okay. Three more things that are really important that you need to know. We have a secant line. A secant goes through your circle, so you can think of secant slices. Okay, so a secant kind of slices through your circle. I usually kind of think of that game Fruit Ninja. Okay, you know how you take the fruit and you slice through it? Well, that's what a secant does. It slices through your circle. Okay. So then we have a point of tangency, which is right here. It's a point on the circle, and that's where your tangent actually touches your circle. Okay, so a tangent touches. So easy way to remember this is, for our chord, we thought of a guitar string. We have a secant line. It slices through the circle. And then we have a tangent, and it actually only touches at one point on my circle. Okay, so a tangent touches. Okay, tangent touches, and that's at one point. Okay, so that's a pretty easy way to remember the difference between those. Chord is like a guitar string. It has its end points on the circle. Secant slices through the circle, and it is a straight line, and then a tangent line touches the circle at one point. Okay. Alright, so now that we know what they are, let's move on to our first example. Okay, so our first example, we want to tell whether the line, whether it's a line, array, or segment is best described as a radius, a chord, diameter, secant, or tangent of circle C. Alright, so our first one is AC. Okay, so AC. AC. And this goes from the center halfway across our circle, and it touches at one point. And so AC happens to be a radius. Okay, so it follows all the characteristics of a radius, so that's what it is. Alright, so if we look at B, if we look at B, it says AB. Okay, so AB. And notice that this is actually a segment, okay? And we have our two endpoints that are on the circle. It goes through the center, so it is actually a chord because we have two endpoints. but it's a special type of chord. Since it goes through the center, it's also the diameter. Alright, so if we look at ray DE, okay, so DE, okay, and if we look at B, it happens to touch the circle just at one point, okay, so since it touches the circle at one point, you think tangent touches, so it's a tangent line. Alright, and the last one, line AE, we have AE, and now we do have two endpoints that are on the circle, but you see how it kind of slices through my circle? So secant slices. So AE is actually a secant line. Okay, hopefully that makes sense and that's pretty easy. Let's go ahead and move on. Alright, so there's a couple different things that you need to know. They're in coplanar circles and common tangents. Let's see, coplanar circles that intersect at one point are called tangent circles. That means they touch at one point. Okay, so these are one point of intersection, so they're tangent circles. Concentric circles are actually ones that have the same center, and it kind of reminds me of a target or a bullseye. So concentric means they have the same center. Okay, and if you take a look over here, we have 2 points of intersection on these two lines. So they just meet twice. Let's see, a line or a segment that is a tangent to two coplanar circles is called a common tangent. A common internal tangent intersects the segment and joins the centers of the two circles, and a common external tangent does not intersect the segment and joins the center of the two circles. Okay. So let's try example 2. It says, drawing and identifying common tangents. Tell how many common tangents the circles have and draw them. Use blue to indicate common external tangents and red to indicate common internal tangents. Alright, so on this, the first thing I'm going to do is redraw all of these. Okay, so once you've redrawn them, the next thing you want to do is connect the centers. Alright, so tangent lines means that they touch the circle at one point. But since we have two circles, it's going to touch at 2 points, but one on each circle. Okay, so we have to use red for the lines that are going to actually cross. So I'm going to have it go straight through here, and see how I made it touch here and touch here, and it's actually a common tangent line between these two circles. And then I'm going to have another one that goes here to here. Okay, so these are internal. It's going in between my two circles. Now, the blue is going to be for ones that are on the same side of my circles, and they're just going to touch on the same side, and they are actually not going to touch the inside of my circles, and they're not going to cross and touch the two lines that are, or the line that's connecting my centers. Okay, so that's how you do B. Alright, so, sorry, that's how you do A. Let's look at B. We're going to connect a line for my centers. Okay, the tangent line that goes between them is red, and that's an internal tangent. Okay, so they touch each of them at one point. And then the blue line indicates the external tangents, meaning they're on the same side, and they still touch at 1 point on each circle. And then the last one, alright, so you start the same way. You connect your two centers. Now there's no way for me to draw a red line because it would end up crossing the two circles twice. So the only way you can draw tangent lines on these is if you have them on the outside, like so. So if you look at A, there was 4 common tangents, B had 3 common tangents, and C only had 2 common tangents. Alright, new theorems. It says any radius in the plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of a circle at its endpoint. Alright, so if you have a tangent line, that means the radius is going to be perpendicular to it always. Okay, and the next theorem says if you have 2 tangent lines and they meet at a certain point, the 2 tangent lines are going to be congruent. And this always reminds me of the Jack-in-the-Box dude, that his hat has to be congruent on both sides, because if it wasn't, you'd have a weird lopsided hat and he would not be okay. Okay, so that doesn't work. You have the Jack-in-the-Box dude and his hat has to be even on both sides. So that reminds me of theorem 10.2. So let's actually try an example of that. It says, verifying tangent to a circle. Well, if ST has to be tangent to circle P, that means this needs to form a right angle. Okay, well that means it's a right triangle. That means it needs to actually fit into Pythagorean theorem. Okay, so a squared plus b squared is equal to c squared. Your c is always across from your right angle, so we have 35 squared plus 12 squared. And we don't necessarily know if it's equal, but we hope it is. Okay, so we know 35 squared is 1,225, 12 squared is 144, and 37 squared is 1,369, and we hope that it's equal. So 1,225 plus 140 is actually 1369, and it is indeed congruent. So we verified it, that this has to be a right triangle. Alright, the next example, it says in the diagram, point B is a point of tangent C, and to find the radius of circle C. Okay, so we know that the radius is perpendicular to our tangent line, so we know that this has to be our right angle, and that this is going to be my hypotenuse. Well, if I think about this whole length here, this is 50 plus r. Okay, now I can actually plug into Pythagorean theorem and solve for r. Okay, so Pythagorean theorem is a squared plus b squared is equal to c squared. Our hypotenuse is across from the right angle, so we know that this is our c. Doesn't matter what you plug in for a and b. We have 80 squared plus r squared is equal to 50 plus r squared. Now, in order to solve this, you have to do 80 squared, which is 6,400, plus r squared. And the way you solve the right part of this equation, you have to think of this as 50 plus r times 50 plus r. You can't just say 50 squared plus r squared. That's not how it works. And then you have to FOIL. Okay, so F-O-I-L, first, outer, inner, last. Okay, so the first terms is 50 times 50, which is 2,500. Okay, the last, or the outer terms, is 50 times r, so that's plus 50r. And then the inner terms is 50 times r. And then the last terms is r times r, which is r squared. Okay, and then you combine like terms, you get 6,400 plus r squared is equal to 2,500 plus, and then you add these together, so you get 100r plus r squared. And then you need to get r's on one side and numbers on the other. So I'm going to subtract r squared from both sides, and they end up canceling out. So I end up getting 6,400 is equal to 2,500 plus 100r. We're going to subtract 2,500 from both sides. I'm going to have a little bit of space, and I get 3,900 is equal to 100r. And then if you divide by 100 on both sides, you get r to be 39. Our last example, it says RS is tangent to circle C at point S, RT is tangent to circle C at T. Find the value of x. Well, here's our jack-in-the-box hat. We know that these two have to be congruent, so that means 3x plus 4 is equal to 28. Subtract 4 on both sides, we get 3x is equal to 24. Divide by 3, we get x equals 8. And that was a pretty straightforward and simple question. Thank you all for tuning in, and I hope you have a great day, and I hope you enjoyed Tim 1.